Okay, we're going to do an optimization problem here, and these are a very important group of problems in mathematics. And in this situation, what we're doing is building a fence along a river, a three-sided rectangular fence enclosing 4,000 square feet is to be built along the side of a river using the least amount of fencing. You might write that down, stop it and write that down if you want to do that and write your picture and everything. So that's what we're trying to do. We're trying to build this fence, and it has to enclose 4,000 square feet. But we want to use the least amount of fencing we possibly can. There's a lot of different ways we could build this. We could build this really long and the width very short, or we could make the width longer, etc. There's a lot of different dimensions we could build this build this fence. So what we're trying to minimize is the perimeter, aren't we? We're trying to really minimize the perimeter. And I'm going to put min here. We're trying to minimize the perimeter. And it's clear that whatever dimensions we pick, it's going to be W plus L. 2W plus the length L. We don't have to worry about the river because it's its own fence, so to speak. And so that's what we're trying to minimize, is this perimeter. And when I look at this equation, I've got too many variables. I've got P, W, and L, and that's too many. And we want to develop another one. We do have another one, that the length times the width has to equal 4,000. So I've got this L sticking out here, so I think I'm going to solve for L. 4,000, okay, over W is what L is. And by the way, this L times W is called the constraint. It constrains how the variables can be. And so I'm going to put in for L 4,000 over W. So I'm going to say the P, what we're trying to minimize, equals 2W plus 4,000 over W. Okay, and we're trying to minimize. We want to minimize this P. Well, here we have a function in two variables. It's a rational function. And this is a comma, by the way, not a point, decimal point. And if we could graph this and take a look at it, we suspect that if there's a minimum, that maybe it's going to look something like this, right? It's going to come down and have a minimum point right there. By the way, W itself has to be greater than 0, right? In fact, W can't equal 0 because it would be undefined. So we suspect that we're going to have something from 0 on, and we're going to have a flat point there. In other words, the derivative is going to be 0 wherever we have the minimum amount of perimeter. If this is P, okay, and this is W in our little graph. So that's what we're looking for. So we're looking for this point W that'll give me the smallest perimeter. So what do we do normally when if we're graphing this? We take the derivative, right? And that's what I'm going to do. P prime, of course, would equal 2 minus, my chalk keeps breaking here, minus 4,000 over W squared, doesn't it? And I think everybody knows how to do this derivative. This is really 4,000 times W to the -1. You bring the -1 out front and subtract another one, -2. You can bring it downstairs. So there we have it. There's our perimeter prime. And we look for places where this might have a local max or a local min, like this. And we look for it, with two places we look are where it's undefined, and you might say, well, shouldn't W at 0, W equals 0, be a critical point? No, W has to be greater than 0, so we can't use that. So wherever this thing equals 0 will give us a critical point. So I'm going to set the derivative to 0, and now I have to solve a little rational equation there. And what I'm going to do is I'm going to need more room, because I'm going to have a suspicion that if I go any farther, and I'm just hoping that that got in too. Let me check. Oh yeah, we're getting it all in. I think I'm going to erase this. Okay, so I assume you've written it down, or you can go back and write it down. You have the luxury of running this thing backwards, and I do not. Okay, so I'm going to go up here. Now I'm going to take this thing and I'm going to go up here. All right. So what I want to do is set this to 0. What I'm going to do in order to do that, I'm going to multiply the lowest common denominator of 2 over 1 in this 4,000 over W squared 0 is W squared. I'm going to multiply each term by W squared. And when I do that, I'm going to get 2W squared minus 4,000. And when I multiply by 0 by W squared, I just get 0. And so I end up with W squared equals 2W squared equals 4,000 positive. And W squared itself equals 2,000. which implies, let me write implies, which implies that W equals the square root, I don't have enough room here, 2,000. Okay, and that comes to about approximately 45 feet. I think it's about 44 point something feet, 8 feet or something. And so that's about 45 when we take the square root of 2,000. So I figure that this W here is about 45 feet. So that should be my width. That's the idea. This would be my width. Now technically I should put this on a number line, check left side, right side, to make sure that you have a negative derivative here and a positive derivative here, so the thing is increasing, decreasing, because this could be a maximum, but I'm pretty sure that that's a minimum. You can check it yourself later. In fact, I know it is. So let me do this here. This is where I'm going. So I went from this equation, I came up here, and I solved the rational equation, and I got 45. Now, how do I find the length? Well, the length is 4,000 over W. So the length is 4,000 over 45, which I believe, when I put it in my calculator, I got around 89. So the length is 89 feet approximately. So if I make my length 89 feet and my width 45, was that at 45? I will use the least amount of, I'll have the smallest perimeter and I'll use the least amount of fencing, and that'll save me some money. And that's what I'm trying to do, is save money by using less fencing, right? Making the perimeter as small as possible.